Imagine standing in a completely dark room holding a flashlight. You turn it on and the beam reveals walls about 30 feet away in every direction. For your entire life, you've assumed this room is the whole world. Then one day, someone hands you a more powerful flashlight. You switch it on and suddenly you see that those walls you thought were the boundaries, they were just curtains. Behind them stretches a space so vast that your new light can't even reach the actual walls. And here's the disturbing part. While you're standing there trying to comprehend this, the real walls are racing away from you faster than your light can travel. This is exactly what happened to humanity in 2024. The James Webb Space Telescope, our new cosmic flashlight, just revealed something that shattered every assumption we had about the universe's size. We thought we understood the scale. We were wrong by a margin so enormous that it breaks our ability to visualize it. The universe isn't just bigger than we thought, it's bigger than we thought was possible. And tonight, you're going to discover just how catastrophically wrong we've been about the true size of everything. Chapter 1. Cosmic Expansion. The answer to why the universe is bigger than its age would suggest requires us to confront something uncomfortable. Space itself is not a fixed stage where events unfold. Space is dynamic, it stretches. And when space stretches, it carries everything embedded in it along for the ride, creating distance without anything actually moving through space in the traditional sense. Let me establish the foundation. In 1929, astronomer Edwin Hubble made an observation that would eventually overturn humanity's entire cosmic framework. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured the light from distant galaxies and noticed something peculiar. The light was shifted toward the red end of the spectrum, and the farther away the galaxy, the more extreme the redshift. This wasn't just random noise in the data, it was a pattern, a relationship. Galaxies twice as far away were receding twice as fast. Galaxies 3 times farther were receding 3 times as fast. This relationship, now called Hubble's law, revealed something extraordinary. The universe is expanding uniformly in all directions. But here's what's crucial to understand. The galaxies aren't flying apart through static space like shrapnel from an explosion. Space itself is expanding, carrying the galaxies with it. Imagine drawing dots on the surface of a balloon, then inflating it. The dots move apart, but not because they're traveling across the balloon's surface. They separate because the surface itself is stretching between them. Now apply this to cosmic scales. A galaxy 1 billion light-years away from us right now is receding at about 70 kilometers per second due to cosmic expansion. That's the Hubble constant, though its exact value is currently under fierce debate in cosmology. A galaxy 2 billion light-years distant recedes at 140 kilometers per second. 4 billion light-years, 280 kilometers per second. You can see where this leads. At some distance, the recession velocity equals the speed of light, roughly 14 billion light-years in current proper distance. Beyond that distance, space between us and those regions is expanding faster than light can cross it. This is not a violation of Einstein's relativity. Nothing is moving through space faster than light. Space itself is stretching, which is not constrained by relativity's speed limit. It's a subtle but crucial distinction. An object embedded in expanding space can be carried away from us at any velocity, even superluminal speeds, without violating physics. The speed limit applies to motion through space, not to the expansion of space itself. To put this in perspective, consider a photon emitted from a galaxy shortly after the Big Bang, heading in our direction. That photon travels through space at exactly light speed, as all photons must, but the space between us and that galaxy is also expanding. For much of cosmic history, that photon was actually losing ground, carried backward by expansion faster than it could make forward progress toward us. Only as cosmic expansion gradually slowed down and dark energy hadn't yet dominated to re-accelerate it, Did that photon finally start making net progress toward Earth? When it finally reaches us 13.8 billion years later, the galaxy that emitted it is no longer 13.8 billion light-years away. It's now 46.5 billion light-years distant, carried there by 13.8 billion years of continuous spatial expansion. This is why the observable universe has a radius of 46.5 billion light-years, giving it a diameter of 93 billion light-years, despite being only 13.8 billion years old. The light reaching us today left sources that are now far more distant than simple multiplication of age times light speed would suggest. Distance in an expanding universe is not static, it's dynamic, contextual, and depends entirely on when you're measuring. Dr. Brian Greene, physicist at Columbia University, describes this realization as the moment cosmology stopped being intuitive. Our everyday experience trains us to think of distance as fixed. If something is 10 miles away, it remains 10 miles away unless one of us moves. But cosmic distance doesn't work that way. A galaxy can be motionless relative to its local space while simultaneously racing away from us at half the speed of light because the space between us is stretching. The 2022 data from the James Webb Space Telescope deepened this mystery considerably. JWST observed galaxies whose light has been traveling for more than 13 billion years, meaning we're seeing them as they appeared just 300 to 500 million years after the Big Bang. But these galaxies appeared far more mature, far more structured than models predicted. They had already formed hundreds of billions of stars. They showed signs of heavy elements that require multiple generations of stellar evolution to create. They were massive, organized, and complex at a time when the universe should have still been relatively simple. This discovery created what cosmologists now call the impossibly early galaxy problem. If these structures formed so quickly, it suggests the universe was somehow more efficient at gravitational collapse and star formation in its early epochs than we understood. Or it suggests that the seeds of structure, the initial density fluctuations that would grow into galaxies, were larger or more pronounced than our inflation models predicted. Either way, it means the universe was busier, more active, more structured at earlier times than we thought possible. Imagine you're watching a time-lapse of a forest growing. You expect to see seeds germinate, saplings slowly grow, and eventually mature trees after decades. But instead, you fast forward past the germination phase and suddenly the forest is already there. Trees 50 feet tall, ecosystem complex and thriving just minutes after the seeds hit the ground. That's what JWST revealed about cosmic structure formation. The forest was already grown when we expected to see saplings. This has profound implications for the universe's actual size beyond what we can observe. If structure formed faster and earlier than expected, it suggests the universe beyond our observational horizon is likely far more populated, far more complex than we projected from our local sample. The observable universe might contain 2 trillion galaxies, but the total universe, the complete cosmos beyond our light horizon, could contain trillions of observable universe-sized regions, each with their own 2 trillion galaxies, stretching in all directions beyond any possibility of detection. You are sitting on a planet, orbiting a star, in a galaxy, within a local group of galaxies inside a supercluster, which is part of the observable universe. And that entire observable universe, this 93 billion light-year sphere containing everything we can ever see or measure, might be just one small region in an infinitely larger cosmos that extends forever in all directions, filled with structures and galaxies and perhaps even intelligent civilizations that we can never contact, never detect, never know about, because the expansion of space itself has placed them beyond the absolute boundary of causality. The universe is not just big in the sense of large, It's big in the sense that it defeats comprehension, that it renders our cosmic neighborhood, vast as it is, into an infinitesimal fraction of what exists. So we've established that space expands, carrying distant objects beyond our reach. But this raises an urgent question. If we can measure light from galaxies 46.5 billion light-years away, what exactly are we measuring? What does distance even mean when space itself is dynamic? Chapter 2. Measurement. Paradox. Distance in cosmology is not one thing. It's at least 4 different things, each valid in its own context, each telling us something different about the universe's structure. Understanding this multiplicity is essential to grasping why astronomers can make seemingly contradictory statements about how far away something is, with all statements being simultaneously true. Let's start with the most intuitive concept: proper distance. This is the distance you would measure if you could freeze the expansion of the universe right now, lay down a measuring tape through space, and count how many light-years separate us from a distant galaxy. For a galaxy whose light has been traveling for 13 billion years, its proper distance today is approximately 32 billion light-years. That galaxy was much closer when it emitted the light we're now receiving. But 13 billion years of cosmic expansion has stretched the space between us, carrying it to its current proper distance. Then there's co-moving distance, which factors out the expansion of the universe entirely. It asks, if we eliminate the stretching of space and measure distance in a coordinate system that expands with the universe, how far away is this object? Co-moving distance remains constant over time for objects moving only due to cosmic expansion. It's the distance cosmologists use when constructing maps of large-scale cosmic structure because it reveals the underlying distribution of matter without the distortion of expansion. Light travel distance is perhaps the most psychologically natural for humans to understand. It's simply how long the light has been traveling to reach us, multiplied by the speed of light. A galaxy whose light took 10 billion years to arrive has a light travel distance of 10 billion light-years. This corresponds to look-back time, telling us how far back into cosmic history we're viewing. But it's not the galaxy's current distance, which expansion has increased substantially since the light was emitted. Finally, there's luminosity distance, which is calculated from how bright an object appears compared to its intrinsic brightness. In an expanding universe, this distance is larger than you'd expect because expansion stretches the wavelength of light, reducing its energy, and spreads out the photons over a larger area. Measuring luminosity distance was how astronomers in 1998 discovered that cosmic expansion is accelerating, a finding that won the Nobel Prize and revealed the existence of dark energy. Dr. Wendy Friedman, who leads the Chicago Carnegie Hubble program, describes these multiple distance measures as different languages for describing the same underlying reality. When you read that JWST detected a galaxy at redshift Z13, that's simultaneously telling you the light travel time, the scale factor of expansion since emission, and indirectly the proper distance today. Each number encodes the same cosmic history from a different mathematical perspective. The 2024 discoveries complicated this picture significantly. JWST found galaxies at redshift values exceeding 14, corresponding to light emitted less than 300 million years after the Big Bang. At those extreme distances, the differences between distance measures become dramatic. A galaxy at redshift Z14 has a light travel distance of about 13.5 billion light-years, but its proper distance today is approximately 47 billion light-years. The space between us and that galaxy has stretched by a factor of 15 since the light began its journey. But here's where measurement becomes genuinely paradoxical. When we observe that distant galaxy, we're seeing it as it was 13.5 billion years ago. We have no information about what it looks like now. For all we know, it could have been destroyed by a collision, consumed by a supermassive black hole, or evolved into something completely unrecognizable. The galaxy we're studying exists only in the past tense, a fossil preserved in ancient light. Consider what this means. Everything you see in the night sky is history. The moon as it was 1.3 seconds ago, the sun as it was 8.3 minutes ago, Alpha Centauri as it was 4.4 years ago, the Andromeda Galaxy as it was 2.5 million years ago. For nearby objects, this delay is trivial, but for distant galaxies, it's profound. When we observe the most distant known galaxy, we're seeing an object as it appeared when the universe was barely 2% of its current age. We're archaeological astronomers studying ancient structures through the fossil record of light. To put this in perspective, imagine you're watching a live stream of an event, but the stream is delayed by several hours. You're seeing everything that happened, but with a time lag. Now imagine that delay increases the farther away the camera is. For cosmic distances, the delay isn't hours, but billions of years. The universe you observe is not the universe as it exists now. It's a patchwork of different eras, with nearby regions showing recent cosmic history and distant regions showing ancient cosmic history, all stitched together into a single, apparent present moment. This creates a strange informational structure. The observable universe forms a light cone in space-time, with us at the apex. Every point on the surface of that cone represents events at a specific cosmic time, progressively earlier as you look farther away. The most distant visible galaxies mark the surface of last scattering, the cosmic microwave background radiation emitted when the universe became transparent 80,000 years after the Big Bang. That surface represents the absolute limit of electromagnetic observation. Before that moment, the universe was opaque, a plasma so dense that photons couldn't travel freely. The Planck satellite, which operated from 2009 to 2013, mapped the cosmic microwave background with unprecedented precision. It revealed tiny temperature fluctuations, differences of only a few millionths of a degree, imprinted on the radiation. These fluctuations are the seeds of all cosmic structure, quantum fluctuations inflated to cosmic scales. During the initial fraction of a second, they tell us the geometry of space, the density of matter and dark energy, and the age of the universe with remarkable accuracy. But they also represent an absolute boundary we cannot see past the CMB with light. It's a cosmic curtain drawn across the first 380,000 years of existence. However, in principle, we could observe farther using neutrinos or gravitational waves. The universe became transparent to neutrinos when it was only 1 second old. A cosmic neutrino background should exist, analogous to the CMB, but from an even earlier epoch. Detecting it would push our observational horizon back to the first second of cosmic history. Gravitational waves could theoretically carry information from even earlier times, potentially from the inflationary epoch itself, trillionths of a second after the Big Bang. You might wonder why this matters, why we should care about observational horizons and different types of distance. Here's why. These measurements determine what we can ever know about the universe's true extent. The observable universe is not synonymous with the universe. It's only the region within our past light cone, the zone from which light has had time to reach us. The actual universe could be vastly, perhaps infinitely, larger. Or it could be finite, but curved back on itself. We don't know, and within the observational constraints of light speed and cosmic expansion, we may never know for certain. What we do know is this: every measurement we make reveals the universe to be larger, more complex, more structured than the previous measurement suggested. Every technological advance in telescope design pushes the boundary of observation farther, revealing earlier epochs and more distant structures. And every time we push that boundary, we find that the universe was already mature, already busy, already full of galaxies and stars and structure at earlier times than we predicted. The measurement paradox is ultimately this: the better our measurements become, the more we realize how little of the total universe we can ever measure. So if we can only observe a finite region, and even that region is mostly unreachable due to accelerating expansion, what lies beyond our observational horizon? Chapter 3. Beyond Observable. The universe beyond what we can observe is not theoretical speculation. It's a logical necessity, a consequence of cosmic expansion combined with the finite speed of light. There is definitely more universe out there beyond our horizon. The only questions are how much more and what does it look like? Let's establish what we can infer from physics and observation. The observable universe is homogeneous and isotropic at large scales, meaning it looks roughly the same in all directions and at all locations once you average over sufficiently large volumes. This is not a trivial observation. It's strong evidence that the universe extends far beyond what we see, because if the observable universe represented the total universe, we'd expect to see edge effects, boundary conditions, some indication that we're approaching a limit. We see none of that. The universe looks the same in every direction we examine, suggesting we're nowhere near any edge. The cosmic microwave background provides crucial evidence here. The CMB is uniform to 1 part in 100,000 across the entire sky. Regions of the CMB separated by more than a few degrees are not causally connected, meaning they've never been in contact with each other, never exchanged information, yet they have almost exactly the same temperature. This uniformity is explained by cosmic inflation, a brief period of exponential expansion during the first tiny fraction of a second after the Big Bang, which smoothed out irregularities and made causally disconnected regions effectively identical. Dr. Alan Guth, who proposed cosmic inflation in 1980, calculated that if inflation occurred as the theory suggests, the total universe must be at least 1023 times larger than the observable universe, and possibly infinite. That's not 10 times larger or 1,000 times larger. It's 10 with 23 zeros after it times larger. The observable universe would be to the total universe what a single atom is to the Milky Way galaxy, or smaller. Think about what this means in practical terms. If you could somehow travel to the edge of our observable universe, you would not find a wall or a boundary. You would find more galaxies, more stars, more cosmic structure, extending in all directions essentially identical to what we see here. And if you traveled another 93 billion light-years in any direction, you'd find the same thing again, and again, and again. Each region would have its own observable universe, centered on itself, overlapping with ours but extending into regions we can never see. The 2024 data from JWST supports this picture of extended uniformity. The early galaxies JWST detected show the same types of structures, the same general properties as galaxies in our cosmic neighborhood, just caught at earlier evolutionary stages. There's no indication that the universe becomes fundamentally different at extreme distances. It's just younger versions of the same basic patterns we see nearby. But here's where it gets genuinely strange. If the universe is truly infinite in extent, as inflation strongly suggests, then every possible configuration of matter that can exist does exist somewhere out there beyond our horizon. This is not mysticism or speculation, it's a straightforward consequence of infinite space combined with finite possibilities at any given location. Consider there are only so many ways you can arrange atoms in a given volume of space. The number is astronomically large, but it's finite. If you have infinite space, you must eventually repeat every possible arrangement. This means there are other regions of space incredibly distant where matter is arranged in the same configuration as our observable universe. Not similar. Identical. Perfect duplicates, down to every atom in every star, every planet, every living cell. Max Tegmark, cosmologist at MIT, calculated the scale at which you'd expect to find such duplicates. If the universe is infinite and uniform, statistical mechanics predicts you'd find an exact duplicate of our observable universe at a distance of roughly 10 × 10^29 meters away. That's a distance so large you can't write it in any meaningful way. It's not a Google or Googleplex. It's vastly, incomprehensibly larger than such numbers. For practical purposes, these duplicate regions might as well not exist because they're forever beyond any possibility of contact or detection. But the logic is airtight. If space is infinite and matter is finite in its possible configurations, duplicates must exist. This is sometimes called the cosmic copycat problem, and it creates genuine philosophical difficulties for concepts like identity, uniqueness, and free will. If there's another you, identical down to every neuron firing in your brain at this moment, experiencing exactly what you're experiencing right now, making the same choices, having the same thoughts, in what sense are you a unique individual? To put this in perspective that might help you internalize the scale, imagine that every atom in your body is itself a complete observable universe containing 93 billion light-years of galaxies and stars and planets. The distance to your duplicate is larger compared to our observable universe than our observable universe is compared to a single atom. The scales involved make normal human intuitions about size completely meaningless. Yet this is what modern cosmology, built on well-tested physics and observational evidence, logically requires. The universe is not just bigger than we can observe, it's bigger than we can conceptualize, even using mathematics. It may literally be infinite, extending forever in all directions, containing infinite matter and energy, infinite galaxies, infinite stars, infinite planets, infinite complexity beyond any boundary. Some physicists have proposed alternatives to avoid these bizarre implications. Perhaps the universe is finite but unbounded, curved back on itself like the surface of a sphere. If you traveled far enough in one direction, you'd eventually return to your starting point from the opposite direction. This would make the total universe large but finite, avoiding the duplicate problem. However, measurements of the cosmic microwave background have placed tight constraints on cosmic curvature, and current data indicates the universe is spatially flat to within measurement precision. A flat universe, if it has any finite size at all, must be vastly larger than the observable region. Another proposal is that the universe has exotic topology, like a torus or more complex manifold, allowing it to be finite in volume while still being flat. Imagine living on the surface of a donut. You could travel in any direction and eventually return to your starting point, yet locally the surface appears flat. Some cosmologists have searched the CMB for repeated patterns that might indicate such topology, but so far, no convincing evidence has emerged. Consider what you're doing right now as you watch this video. You're sitting on a planet that's one of trillions in our galaxy, which is one of hundreds of billions in our observable universe, which might be one of infinite regions in an infinite cosmos. The very act of being conscious, of experiencing anything at all, is occurring in a specific location within this incomprehensible vastness. You are not at the center because there is no center. You are not near any edge because edges may not exist. You simply are here, now, in this particular bubble of causality, forever separated from most of what exists by the finite speed of light and the expansion of space. This is not a comfortable realization. It's profoundly isolating in some ways, reducing human civilization to a statistical insignificance in the cosmic ledger. But it's also strangely liberating. If the universe is truly this vast, then everything that can happen does happen somewhere. Every story gets told, every possibility gets explored. Existence itself becomes an infinite creative process, endlessly generating novelty and complexity across scales and distances that make our observable universe seem claustrophobic by comparison. What makes this realization urgent now is that the universe is not static, it's evolving, and that evolution has a direction. Which brings us to the most troubling aspect of cosmic scale, time. If the universe is this vast in space, how vast is it in time? How long will it last? Chapter 4. Temporal Immensity. When we talk about the universe being 13.8 billion years old, we're discussing its past, but that's merely the prologue. The universe's future timeline dwarfs its history by margins that make spatial scales seem modest. We are living in the first eye blink of a story that will continue for timescales that mock human comprehension. Let's establish the framework. The universe began in an extremely hot, dense state 13.8 billion years ago. For the first few 100 million years it was dark, filled with neutral hydrogen gas gradually collapsing under gravity. Then the first stars ignited, fusing hydrogen into helium, flooding the cosmos with ultraviolet radiation that ionized the gas. Galaxies formed, merged, created large-scale structure. For the past few billion years, the universe has been in what cosmologists call the stelliferous era, the age of stars, when stellar fusion dominates energy production and structure formation. But stellar fuel is finite. Stars are powered by nuclear fusion, converting light elements into heavier ones and releasing energy in the process. The smallest stars, red dwarfs with masses around 8% that of our Sun, burn hydrogen so slowly they could shine for 10 trillion years. That's roughly 1,000 times longer than the current age of the universe. These miserly stars will be the last ordinary stars to burn, keeping the universe dimly lit long after massive, bright stars have exhausted their fuel and died. Dr. Fred Adams at the University of Michigan has mapped out the universe's timeline across unimaginable durations. According to his models, star formation will peak and then gradually decline as galaxies exhaust their supplies of hydrogen gas. By around 100 trillion years from now, the last stars will wink out. The universe will enter what Adams calls the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. Consider the scale of that transition. Humans have existed as a species for perhaps 300,000 years. Recorded civilization spans roughly 6,000 years. The entire history of complex life on Earth covers maybe 600 million years. That's all background noise, statistical fluctuation, compared to the 100 trillion year lifespan of the stelliferous era. If the current age of the universe were compressed into a single day, stellar civilization would continue for the next 20,000 years. To put this in perspective that connects to your experience, imagine your entire life as a single heartbeat. 100 trillion years would be like 10 million human lifetimes end to end. Every person who's ever lived, every civilization that's risen and fallen, every star you can see in the night sky, all of it occurs in the first fraction of a percent of the time stars will shine. We are living in the extreme youth of the cosmic story, so early that we cannot yet see what the universe will become. But the degenerate era is not the end, it's just another transition. White dwarfs will slowly cool, radiating away their residual heat over time scales measured in quadrillions of years, becoming black dwarfs, objects theoretically predicted, but which don't yet exist anywhere in the universe because insufficient time has passed for even one white dwarf to cool completely. Neutron stars will undergo similar slow fading. Black holes will persist, pulling in stray matter, occasionally merging with each other, growing larger. Then, on timescales around 10⁻40 years, protons themselves may decay. This is theoretical, not yet observed, but many physics models predict that protons, the building blocks of ordinary matter, are not truly stable over infinite time. If proton decay occurs, all remaining matter composed of atoms will slowly disintegrate. Stars' remnants will evaporate, planets will dissolve. Every physical structure composed of protons will cease to exist, leaving only black holes, electrons, positrons, neutrinos, and photons as the remaining constituents of reality. The universe enters what Adams calls the black hole era, lasting from around 10⁻40 years to 10⁻100 years. During this epoch, black holes are the dominant massive objects, but even they are not eternal. Stephen Hawking proved in 1974 that black holes radiate energy through quantum effects at their event horizons, a process now called Hawking radiation. This causes black holes to slowly evaporate, losing mass over time. The evaporation rate depends on mass. Small black holes evaporate quickly. Stellar mass holes take around 10 pr/67 years, and supermassive black holes at galaxy centers take up to 10-100 years. When the last black hole finally evaporates, the universe transitions to the dark era, consisting only of a thin soup of photons, neutrinos, electrons, and positrons, all separated by vast distances, all moving apart due to cosmic expansion, the temperature of space asymptotically approaching absolute zero. Dr. Katie Mack, cosmologist at North Carolina State University, describes this endpoint as the heat death of the universe, a state of maximum entropy where no free energy remains to do work, no structures can form, no information can be processed. It's not destruction in the sense of annihilation, it's the universe slowly running down like a clock winding down until nothing changes anymore because there's no energy available to drive change. But here's what makes 2024's discoveries relevant to this temporal immensity, parole. The detection of impossibly early galaxies by JWST suggests the universe was more efficient at structure formation than models predicted. If structure forms faster, it also might last longer, or transition into new forms we haven't anticipated. The finding that dark energy dominates cosmic expansion and is causing acceleration means the future evolution might be more complex than simple heat death. Some models now propose that dark energy could strengthen over time, leading not to heat death, but to a big rip, where accelerating expansion eventually tears apart galaxies, then stars, then planets, then molecules, then atoms, then atomic nuclei, until finally space-time itself is shredded at the quantum scale. This would occur in perhaps 100 billion years, dramatically shortening the stelliferous era and preventing the slower unwinding of proton decay and black hole evaporation. Other models suggest dark energy could weaken or even reverse, causing cosmic expansion to slow stop and reverse into a big crunch, with all matter and energy eventually collapsing back into a singularity, possibly triggering a new Big Bang and creating a cyclical universe that bounces between expansion and contraction indefinitely. This would make cosmic history not a single linear timeline, but an infinite sequence of cosmic cycles, each potentially with different physical laws and constants. Imagine standing at the beginning of a road that stretches farther than you can see, knowing that what you see is only the first millimeter of a journey spanning thousands of miles. That's humanity's position in cosmic time. We exist at the very start, in the brief epoch when stars shine brightly, when galaxies are distinct and separated, when complex structures exist and evolution is possible. Everything we've ever seen or studied or experienced happens in the cosmic equivalent of the first second after hitting play on a movie that will run for trillions of years. You are not just living in a vast universe. You're living in a vast temporal story, one that's barely begun, whose ending is so distant that we can barely speculate about it using our best physics. The stars you see tonight are temporary features, bright lights that will fade, leaving behind darkness so complete and cold that it will persist for durations that make the entire stelliferous era seem like a brief flash. This temporal perspective fundamentally changes what it means to say the universe is big. Big in space is almost trivial compared to big in time. The spatial distances we've discussed, as incomprehensible as they are, can in principle be crossed given enough velocity, but temporal distances cannot be compressed or traversed. They must be weighted through second by second with no shortcuts. And the temporal distances ahead dwarf the spatial ones by margins that strain mathematics itself. So we live early, in a bright epoch, in a universe still young and vigorous. But even in this early stage, something is happening that limits what we can ever reach. The universe isn't just expanding, it's accelerating, driven by dark energy, creating an ultimate horizon beyond which we are forever trapped. What does it mean to be imprisoned by the expansion of space itself? Chapter 5. Acceleration Risen. In 1998, two independent teams of astronomers studying distant supernovae made a discovery so unexpected that it initially seemed like experimental error. They were measuring how cosmic expansion had changed over time by observing Type Ia supernovae, stellar explosions so uniform in brightness they can be used as standard candles to calculate distance. The expectation was simple: expansion should be slowing down due to gravity pulling everything back together. The farther back you look, the faster expansion should have been. Instead, they found the opposite. Distant supernovae were dimmer than expected, meaning they were farther away than standard cosmology predicted. Expansion wasn't slowing down, it was speeding up. The universe's expansion rate has been accelerating for roughly the past 5 billion years, driven by something we now call dark energy, but don't fundamentally understand. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery, which overturned cosmological models and revealed that dark energy constitutes about 68% of the universe as total energy density. Dark energy behaves like a repulsive force, pushing space to expand faster and faster, overwhelming the attractive force of gravity on cosmic scales. Let's examine what acceleration means for cosmic horizons. In a universe with decelerating expansion, distant objects would eventually become reachable if you waited long enough. Light from increasingly distant galaxies would eventually make its way to us. But in an accelerating universe, the opposite occurs. Regions that are currently observable will eventually cross a boundary beyond which their light can never reach us, no matter how long we wait. This boundary is called the cosmic event horizon, analogous to the event horizon of a black hole. Just as nothing can escape from inside a black hole's event horizon, nothing can reach us from beyond the cosmic event horizon. It's currently located at about 16 billion light-years away in comoving distance, which corresponds to a proper distance today of about 48 billion light-years. Here's what's disturbing about this horizon. Galaxies that are currently visible to us, that we can photograph and study right now, are crossing it as we speak. They're being carried beyond the boundary by accelerating expansion, disappearing from our observable universe forever. In a very real sense, the observable universe is shrinking in terms of what we can ever interact with, even as it grows in spatial extent. Dr. Lawrence Krauss, in his 2012 book, A Universe from Nothing, calculated the implications with disturbing precision. Currently, we can observe about 2 trillion galaxies, but of those 2 trillion, 94% have already crossed the cosmic event horizon. If we launched a spacecraft today, traveling at the speed of light, aimed at one of those galaxies, the spacecraft would never arrive. It would chase that galaxy forever, making progress through space, but losing ground to the expansion of space itself, like running on a treadmill that's accelerating faster than you can run. Only about 6% of currently observable galaxies remain within our causal reach. That's roughly 120 billion galaxies that we could, in principle, send a signal to and have that signal eventually arrive. Every other galaxy we can see is already gone in any meaningful sense, visible only as ancient light, completing its journey from a source we can never touch. To put this in perspective, imagine you're on an island surrounded by ocean and the water level is rising. You can see other islands in the distance, but the rising water is carrying them away faster than you could swim to reach them. One by one, those islands drop below the horizon, disappearing forever. You remain on your island, your visible horizon shrinking, the separation between islands growing until you're completely isolated. surrounded by water, extending forever in all directions, with no other land in sight. That's our cosmic future. The local group, consisting of the Milky Way, Andromeda, Triangulum, and several dozen dwarf galaxies, will remain gravitationally bound, eventually merging into a single, massive elliptical galaxy, sometimes called Milkomeda. But everything beyond the local group will fade from view. The Virgo supercluster, the cosmic web of galaxy filaments and voids, the vast large-scale structure we've spent decades mapping, all of it will recede beyond the cosmic horizon. In about 100 billion years, an observer in the Milkomeda galaxy will look out and see nothing but darkness beyond their own local galaxy. The cosmic microwave background radiation will have redshifted so much that it becomes undetectable. All evidence of the Big Bang, of cosmic expansion, of the existence of billions of other galaxies will have vanished. A future civilization arising at that time would have no way to discover that their galaxy exists in a larger universe. They would appear to live in a static island universe, alone in infinite darkness, with no evidence that anything exists beyond their shores. This creates what cosmologists call the information apocalypse. The universe is not just expanding, it's erasing its own history, destroying evidence of its own structure, limiting what future intelligences can ever learn about cosmic origins and evolution. We are living in a privileged epoch, early enough that we can still see the cosmic microwave background, still detect distant galaxies, still piece together the history of cosmic expansion. Future civilizations will lack this privilege. But the prison goes deeper. The 2024 measurements from the Dark Energy Spectroscopic Instrument, or DESI, which has mapped tens of millions of galaxies to measure cosmic expansion history, revealed something unexpected. The strength of dark energy may be changing over time. If dark energy is strengthening, acceleration will increase, bringing the Big Rip scenario closer. If it's weakening, we might avoid heat death for longer. Either way, the data suggests dark energy is not simply a cosmological constant, as Einstein originally proposed, but something dynamic, something that evolves. Dr. Neta Barkal at Princeton has studied the implications of various dark energy models. In some scenarios, the acceleration could strengthen so much that within 20 billion years, galaxies beyond our local group would be receding faster than light speed already is, and within 50 billion years, the increased expansion could begin tearing apart gravitationally bound structures themselves. Solar systems would be ripped apart. Planets would be pulled from their orbits. Eventually, molecules and atoms would be shredded. Consider what this means for any form of life or intelligence trying to persist on cosmic timescales. You're not just limited in where you can travel by the speed of light. You're actively imprisoned in an ever-shrinking bubble of causality, with most of the universe not just unreachable, but disappearing from view entirely. Any attempt to build a galactic civilization must race against cosmic expansion, establishing outposts in distant galaxies before they cross the event horizon and become forever inaccessible. Imagine you're a consciousness that could survive for trillions of years, perhaps uploaded into some form of computational substrate that doesn't age. You watch as the universe empties around you, as galaxy after galaxy fades from view, as the night sky grows darker and darker until finally only your local gravitationally bound cluster remains an island of matter in an increasingly empty cosmos. You are not dying, the universe is not ending, but you are being isolated, surrounded by an expanding void that grows faster than you can cross it. Trapped in a prison with walls that are simultaneously everywhere and nowhere, made not of matter but of space-time itself expanding at superluminal speeds. This is not theoretical horror, this is the measured, calculated future of cosmic structure based on our best observations and physics. The acceleration is real, the event horizon is real. The shrinking of the causal universe is happening right now, this second, as space expands and carries distant galaxies across that boundary. You might wonder if there's any escape, any loophole in physics that might allow faster-than-light travel or communication. Various theoretical proposals exist: wormholes, warp drives, quantum entanglement. But every serious examination of these ideas reveals obstacles. Wormholes require exotic matter with negative energy density, which may not exist. Warp drives similarly need negative energy and would require more energy than is available in multiple galaxies. Quantum entanglement does not allow faster-than-light communication because extracting the correlated information requires classical communication channels limited to light speed. The speed limit appears to be absolute, not a technological barrier, but a fundamental feature of space-time itself. And if the speed limit is real and cosmic expansion is accelerating, then the prison is inescapable. We are genuinely, permanently confined to an ever-shrinking region of cosmic causality, able to observe a universe we can never touch, surrounded by galaxies we can photograph but never visit, witnesses to a vastness we cannot reach. So we've established that most of the universe is already beyond our reach, and the portion we can interact with is shrinking. But before we explore what this means philosophically, we need to address an even stranger question. What if the universe is not just bigger than we can reach, but bigger than we can observe even in principle? Chapter 6. Observable limits. The observable universe has absolute boundaries set by physics, not by technology. No matter how powerful our telescopes become, no matter how long we wait, there are regions of space-time from which information simply cannot reach us. These boundaries define the ultimate limits of human knowledge about cosmic structure. Let's start with the most obvious barrier, the cosmic microwave background. This radiation, emitted 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, represents the surface of last scattering for photons. Before this moment, the universe was opaque, a dense plasma that scattered photons before they could travel any significant distance. We cannot see past the CMB with electromagnetic radiation because no photons from earlier times could propagate freely. But the CMB is not the earliest possible observation. In principle, we could detect earlier epochs using neutrinos or gravitational waves. The universe became transparent to neutrinos when it was only 1 second old, creating a cosmic neutrino background analogous to the CMB, but from an earlier time. Detecting this neutrino background would be extraordinarily difficult because neutrinos interact so weakly with matter, but it's not impossible. Several experiments, including Ptolemy in Italy and Katrin in Germany, are attempting to develop the sensitivity needed to detect cosmic neutrinos directly. Gravitational waves offer an even earlier window. The universe was never opaque to gravitational waves because they interact with matter even more weakly than neutrinos. In principle, gravitational wave astronomy could observe the universe back to the Planck time, around 10,043 seconds after the Big Bang, the earliest moment at which our current physics can meaningfully describe what was happening. The Planck time represents a genuine boundary, not just of observation, but of physics itself. At earlier times and smaller scales, quantum effects of gravity become dominant, and we lack a theory of quantum gravity to describe what occurs. General relativity breaks down. Quantum mechanics as currently formulated doesn't apply. The very concepts of space and time become fuzzy, indefinite, possibly meaningless. Dr. Abhay Ashtekar, developer of loop quantum gravity theory, describes the Planck scale as the shore of the ocean of quantum geometry, where the smooth space-time of Einstein gives way to a discrete, foamy structure at the smallest scales. What happened before the Planck time, or even whether what before t, is a meaningful concept when time itself might not exist in its usual sense, remains deeply uncertain. But there's another more subtle boundary to observability, the cosmic event horizon created by accelerating expansion. As we discussed, this horizon currently sits at about 16 billion light-years in co-moving distance. Light emitted from galaxies beyond this boundary today will never reach us, no matter how long we wait. The expansion of space carries them away faster than light can close the gap. This creates a permanent informational barrier. We can observe galaxies that are now beyond the event horizon because we're receiving light they emitted in the past before they crossed it. But we cannot observe their current state, and we never will. Any events occurring in those galaxies today, any supernovae exploding, any civilizations arising, any physical processes unfolding, are forever hidden from our view. To put this in perspective, imagine you're watching a live broadcast from someone walking away from you. As they get farther away, the signal takes longer to reach you, so you're seeing them with increasing delay. Now imagine they're walking so fast that the distance between you grows faster than the signal can travel. Eventually, they cross a boundary beyond which no new signals can reach you. You can still see the old broadcasts completing their journey, but they're showing progressively older scenes. The last image you ever receive is frozen at the moment they cross the boundary, and then it fades to static, and that's what's happening with distant galaxies. We're seeing them as they were in the past, and as they approach and cross the cosmic event horizon, we see them at progressively earlier stages of their evolution, increasingly redshifted, dimming and fading, until they eventually disappear entirely. The last photons from those galaxies are completing their journey now, stretched by expansion into microwaves, then radio waves, then wavelengths too long to detect. The 2023 results from the Euclid Space Telescope, which is mapping the geometry of the universe and the distribution of dark matter, confirm that the event horizon is a real physical boundary moving through space. Euclid detected galaxies right at the edge, the most distant structures we can ever observe, beyond which the accelerating expansion has created an impassable barrier. This raises a profound question. If there are absolute limits to observation, how can we claim to know anything about the total universe beyond those limits? The answer is we extrapolate based on uniformity. Everywhere we look, the universe appears homogeneous and isotropic at large scales. The same types of galaxies, the same physical laws, the same fundamental constants operate everywhere we observe. It's reasonable to infer that this uniformity continues beyond our observational horizon. But reasonable inference is not the same as direct observation. There could be regions of the universe beyond our light cone where physical constants are different, where different laws of physics operate, where matter behaves in ways we've never observed. The anthropic principle suggests we must live in a region where physics allows complex structure and life to arise, but that doesn't tell us what conditions exist in regions we cannot see. Some inflationary models predict a multiversid structure where different regions of the total cosmos underwent different histories during inflation, resulting in different physical properties. These pocket universes, or bubble universes, would be causally disconnected from each other, each potentially with different values for fundamental constants, like the strength of gravity, the mass of the electron, or the cosmological constant. Dr. Andre Linde at Stanford, one of the architects of inflationary theory, describes this as eternal inflation, where inflation never truly ends but continues in different regions, spawning infinite bubble universes with diverse properties. Our observable universe would be just one bubble among infinite others, each isolated by superluminal expansion, each potentially developing different structures and governed by different physics. If eternal inflation is correct, then the observable universe represents an infinitesimal fraction, not just of the spatial extent of our universe, but of the total ensemble of universes. The limits to observability don't just hide distant regions of our cosmos, they hide entire alternate cosmoses with potentially unimaginable properties. Consider what you're experiencing right now. You're receiving photons from the sun emitted 8 minutes ago. You're receiving photons from distant galaxies emitted billions of years ago. evolve. Every observation you make is historical, showing you the past state of distant objects. But there's a deeper layer. The observations themselves are limited to a specific, finite region of space-time, the interior of your past light cone. Everything outside that cone is invisible to you, not just now, but forever, unless you move or wait for more information to arrive. You are not observing the universe. You are observing your observable universe, the specific subset of reality that has had causal contact with your world line through the history of cosmic expansion. An observer in a distant galaxy has a different observable universe, overlapping with yours but extending into regions you can never see. Every observer has their own unique observable universe, and as expansion continues, these observational bubbles grow in spatial extent but shrink in the number of galaxies they remain causally connected to. This creates a strange kind of perspectival relativity. There is no God's eye view of the total universe, no perspective from which everything is simultaneously visible. Every possible viewpoint is limited, constrained by light speed and cosmic expansion. The total universe, if it exists as a meaningful concept, is the union of all possible observable universes, a structure that can never be directly observed from any single location. The boundary between known and unknown is not a distant frontier we might someday reach with better technology. It's a fundamental, permanent feature of cosmic structure. The universe has drawn a line marked by the speed of light and the expansion of space, beyond which information cannot pass. We can map that line, calculate its location, understand its properties, but we cannot see past it. So we live in a cosmos that's almost entirely hidden from us, where most of what exists is behind observational horizons we can never cross. But that raises perhaps the most disturbing question of all. If we can't see most of the universe, how do we know how big it actually is? Chapter 7. True Scale. The honest answer is we don't know the universe's total size. We can't know given the observational boundaries we've discussed, but we can establish lower bounds, minimum sizes based on what we do observe, and we can make informed inferences based on theoretical models. Both approaches reveal scales that dwarf even the observable universe. Let's start with direct observational constraints. The cosmic microwave background, mapped by the Planck satellite with exquisite precision, shows that the universe is spatially flat to within about 0.4% measurement uncertainty. Flatness has profound implications for total size. If the universe is perfectly flat and infinite, it extends forever in all directions with no boundary. If it's slightly curved, closed like the surface of a sphere, it must be at least several hundred times larger than the observable region to appear this flat from our perspective. Think of it like standing on Earth's surface. Locally, the ground appears flat. Only by traveling great distances or making careful measurements do you discover the curvature. Similarly, if the universe has curvature, it must be curved over scales much larger than what we can observe for that curvature to be undetectable within our measurement precision. Dr. Neil Cornish at Montana State University has analyzed the CMB data to look for signs of cosmic topology, repeated patterns that might indicate the universe wraps back on itself. If the universe were relatively small and closed, light would have had time to circle it multiple times, creating repeating patterns in the CMB. No such patterns have been found, which places a lower limit on the universe's size. It must be at least several hundred times larger than the observable region, giving a minimum diameter of around 30 trillion light-years. But that's just the minimum if the universe is closed. If it's flat and infinite, as current data slightly favors, then there is no maximum size. The universe simply extends forever, containing infinite matter and energy, infinite galaxies, infinite stars, infinite complexity beyond any number you can write or conceive. Inflation theory provides another line of evidence. The inflationary models that best match observational data predict that the universe underwent exponential expansion during the first tiny fraction of a second. growing by at least a factor of 10^26 in size. If the pre-inflationary universe had any finite size at all, even as small as the Planck length, inflating it by this factor produces a total universe at least 10 to 23 times larger than the observable region. Alan Guthr's original calculations suggested an even more dramatic expansion. If inflation lasted just slightly longer than the minimum required to explain the uniformity we observe, the total universe could be 10^10^7 times larger than the observable region. That's not a typo. It's a number so large it requires exponential notation with multiple layers of exponentiation. You cannot write it out. You cannot meaningfully visualize it. It's a scale that makes the observable universe seem smaller than a single atom compared to the Milky Way. The 2024 data from JWST indirectly supports these enormous scales. The fact that early galaxies formed so quickly and appear so mature suggests the universe beyond our horizon likely contains similar structures, extending the patterns we see here across vastly larger regions. The universe does not appear to have any special properties at extreme distances that would indicate we're near a boundary or transition zone. To put this in perspective, using a scale model, imagine shrinking the observable universe down to the size of a marble, about 1 centimeter across. If the universe is minimum sized based on flatness constraints, the total universe would be a sphere about 10 meters across. If inflation produced a factor of 10^23 expansion, the total universe would be vastly larger than Earth's orbit around the Sun. If Guthr's extended inflation is correct, the total universe would be incomprehensibly larger than that, extending across scales that have no meaningful comparison to anything in human experience. But here's what makes 2024's revelations critical. We discovered that even our observable universe is bigger than we calculated. The improved measurements of cosmic expansion rates, the detection of extremely distant galaxies, the refined understanding of how dark energy has evolved over time, all of these push the boundaries farther. Every refinement in measurement, every improvement in telescope technology reveals more structure at greater distances, pushing back our horizon and demonstrating that the universe continues to be larger and more complex than previous estimates suggested. Dr. Wendy Friedman's team, using data from JWST and the Hubble Space Telescope, recently refined the Hubble constant measurement, the rate at which the universe is expanding. Their results show tension with measurements from the cosmic microwave background, suggesting either systematic errors in one approach or new physics we don't understand. But regardless of which measurement is correct, both indicate a universe that's been expanding for 13.8 billion years and is now at least 93 billion light-years across, with the true total size likely orders of magnitude larger. Consider what this means practically. When you look at the night sky, you're seeing perhaps a few thousand stars with the naked eye, all of them in our local cosmic neighborhood within a few hundred light-years. With binoculars, you might see the Andromeda Galaxy, light from 2.5 million years ago. With a small telescope, you can detect objects millions of light-years away. The Hubble Space Telescope captured the Hubble Ultra Deep Field, an image containing 10,000 galaxies in a tiny patch of sky, some over 13 billion light-years distant. Every increase in observational power reveals more structure at greater distances, and that structure shows no signs of ending at the edge of what we can detect. The universe doesn't fade out or become simpler at extreme distances. It remains complex, filled with galaxies and stars and structure all the way to the observational horizon. The most reasonable inference is that this complexity continues beyond what we can see, extending perhaps infinitely in all directions. You are not just looking at a large space, you're looking at a window into infinity, or something so large that the distinction between extremely large and infinite becomes practically meaningless. The observable universe, as vast as it is, might represent such a tiny fraction of the total that our existence, our entire civilization, every galaxy we can see, All of it combined amounts to less than a single grain of sand on all the beaches of Earth. This scale has philosophical implications that we'll explore shortly, but first appreciate the raw fact of it. The universe is bigger than 13.8 billion light-years in radius. It's bigger than 93 billion light-years across. It's probably bigger than trillions of light-years in every direction. It might be infinite. And even if it's finite, it's so large that we will never observe most of it, never interact with it, never know what structures exist in those distant regions, never contact whatever complexity has arisen there. The true scale is not just beyond human comprehension, it's beyond the comprehension of any intelligence operating under the laws of physics as we understand them, and because the scale is so large that gathering information about the whole would require more time and energy than the universe makes available. So we've established that the universe is unimaginably vast, mostly beyond our observational and causal horizons, perhaps infinite in extent. But this raises a question that's haunted philosophy and science for centuries. If we're this small in something this large, does any of it matter? Chapter 8. Significance. Paradox. The universe's scale creates what philosophers call the problem of cosmic significance. If we're infinitesimal fractions of an incomprehensibly vast cosmos, if our entire observable universe might be a negligible speck in something vastly or infinitely larger, if everything we do occurs within a bubble that's shrinking in causal reach and will eventually be isolated in darkness, what meaning can our actions possibly have? This is an abstract philosophy. It's a genuine psychological challenge that many people face when confronting cosmic scales for the first time. The feeling has a name, the overview effect, typically experienced by astronauts seeing Earth from space, realizing how small and fragile our planet appears against the vastness. But the cosmic scale effect goes much deeper, replacing even the solar system and galaxy with something so large it makes those structures seem claustrophobic. Let's examine this paradox carefully. On one hand, size seems correlated with significance. Larger things appear more important than smaller ones. A galaxy seems more significant than a planet. A supercluster seems more significant than a galaxy. By extension, the universe as a whole would be maximally significant, and any particular structure within it proportionally insignificant. But this logic contains a hidden assumption that physical size determines value. Is that actually true? Consider a single neuron in your brain versus the entire Andromeda galaxy. The neuron is incomprehensibly smaller, yet which one is generating subjective experience right now? Which one is aware of anything? The galaxy, for all its billions of stars and trillion solar masses, doesn't think, doesn't feel, doesn't experience. The neuron, for all its infinitesimal size, participates in creating consciousness. Dr. Sean Carroll, physicist at Johns Hopkins, has written extensively about this paradox. He argues that significance is not an intrinsic property of physical systems, but an emergent one, arising from complexity and organization rather than mere size. A human brain, though small, is far more complex than a galaxy, with more information processing occurring in its neural networks than in all the gravitational interactions of a billion stars. The 2024 discoveries deepen this paradox rather than resolving it. JWST's detection of early galaxies shows that complexity arises quickly in cosmic history, suggesting the universe is efficient at creating structure. But it also shows that this structure is occurring across unimaginable scales, in billions of galaxies scattered across vast distances, many already beyond our causal reach. If complexity is common, if structure forms readily throughout the cosmos, does that make any particular instance of complexity less special? Consider two possibilities. First, intelligent life is rare, perhaps unique to Earth in our observable universe. In this scenario, human consciousness might be the only awareness in 93 billion light-years of space, the only perspective from which the universe is being observed and understood. This would make humanity astronomically significant despite our small physical size, because Consciousness itself would be the rarest thing in the cosmos, a unique emergent property that transforms meaningless physical processes into experienced reality. Second possibility: intelligent life is common, arising readily wherever conditions allow. The universe might contain billions of civilizations scattered across billions of galaxies, each one observing their local corner of the cosmos, developing science and philosophy asking the same questions we're asking now. In this scenario, humanity is not unique. We're one instance of a pattern that repeats throughout space, perhaps infinitely many times if the universe is infinite. Which scenario makes us more or less significant? The question itself might be malformed. Significance isn't a conserved quantity that gets diluted across instances. If there are a billion conscious civilizations, each one still generates genuine subjective experience, still creates meaning through awareness and choice, still matters to itself regardless of how many others exist. To put this in perspective closer to your immediate experience, consider your own significance. You are one of 8 billion humans currently alive. Does the existence of those other 8 billion make you less significant? Not to yourself, certainly. Your subjective experience is complete and total regardless of how many other subjective experiences exist simultaneously. The same logic applies at cosmic scales. The existence of other instances of consciousness, if they exist, doesn't diminish the reality and significance of your own awareness. But there's another dimension to this paradox. The universe's scale means that most of what exists is forever beyond our reach and knowledge. Events are occurring right now in distant galaxies 13 billion light-years away that we cannot observe, cannot affect, cannot ever know about. Does something that happens in a region of space we can never interact with matter to us? Dr. David Chalmers, philosopher at New York University, has explored this question in the context of consciousness and causality. He argues that mattering is relational. It depends on connections and interactions. Something can matter tremendously within its local causal network while being completely irrelevant to distant, causally disconnected regions. This suggests significance is not a global property but a local one, meaningful within bounded networks of interaction. Think about your daily life. Events happening right now on the opposite side of Earth might not directly affect you, but they could indirectly through chains of causality, economic connections, information networks, environmental systems. Events happening in another galaxy have essentially zero causal connection to you. They're as irrelevant to your life as events that never happened at all. The cosmic expansion that isolates distant regions doesn't just create physical separation. It creates complete causal disconnection, making those regions literally meaningless to your local causal network. This creates a strange resolution to the significance paradox. You don't have to be significant to the universe as a whole to matter. You only have to be significant within your local causal network, and that network is bounded by light speed and cosmic expansion. The human civilization, all of human history and culture and thought, exists within a specific location in space-time with specific causal connections. We matter to each other, to our local cosmic neighborhood, to the Earth's biosphere, to the future trajectory of technology and consciousness that might spread from our origin. The universe's vast scale, rather than diminishing this significance, actually protects it in a strange way. Because most of the universe is causally disconnected, what happens here genuinely matters here without needing validation or permission from distant regions. We're free to create meaning locally without worrying about cosmic insignificance, because the cosmic whole is too large and too disconnected to impose any external standard of significance. Consider what you're doing as you engage with this information. You're experiencing curiosity, wonder, perhaps some existential unease at contemplating these scales. That experience is real. It's happening in your neurons right now, patterns of electrical and chemical activity creating subjective awareness. The fact that those neurons are tiny compared to galaxies doesn't make the experience less real or less significant. If anything, it makes it more remarkable because consciousness is apparently rare and difficult in the universe. Requiring very specific conditions to arise, while galaxies and cosmic structure are common, forming readily wherever matter and gravity interact. You are not insignificant because you're small. You're significant because you're complex, because you're aware, because you're capable of understanding these scales and asking questions about meaning and value. The universe, for all its vastness, is mostly empty space punctuated by relatively simple structures following relatively simple laws. Consciousness is different. It's complex in ways that dwarf physical complexity, creating internal states that model and represent the external universe, generating meaning and purpose through its own activity. So the significance paradox resolves into something unexpected. Size doesn't determine significance. Complexity, awareness, and local causal connection do. You don't need to matter to the cosmic whole to matter. You just need to matter within your network of interactions, and you clearly do, because you're participating in that network right now by choosing to engage with these ideas. But this resolution opens another question, perhaps the deepest one. If we're isolated in our local causal bubble, if most of the universe is forever beyond our reach, what's our relationship to that larger whole? Chapter 9. Connected. Isolation, we live in a profound paradox, utterly connected to the universe while simultaneously isolated from most of it. Every atom in your body was forged in stellar cores or supernova explosions. You are literally made of processed star matter, scattered into space by dying stars, collected into the cloud that formed our solar system, incorporated into Earth, cycled through ecosystems, and assembled into the structure of your body. You are not separate from the universe. You are a temporary local configuration of universal matter and energy. Yet that same universe has imposed absolute boundaries on what you can interact with. Light speed limits communication and travel. Cosmic expansion creates event horizons that isolate causal regions. The universe that made you has also imprisoned you in a specific location in space-time, surrounded by an observable bubble beyond which information simply cannot reach you. No matter how long you wait, let's explore this connected isolation carefully, because understanding it changes how you relate to cosmic scale. The connection runs deep, far deeper than most people realize. Not only are your atoms recycled star material, but the elements themselves were created in specific stellar environments. Hydrogen, the simplest element, formed in the first few minutes after the Big Bang. Helium and trace lithium also formed then, but everything heavier. Carbon, nitrogen, oxygen, iron, calcium, phosphorus. Every element essential to life and technology was forged in stars. Carl Sagan famously said, "We are made of star stuff, but the specifics are even more poetic. The carbon in your cells was created in red, giant stars through triple alpha fusion, a delicate process requiring precise conditions. The oxygen you breathe was produced in massive stars near the ends of their lives. The iron in your blood was created in supernova explosions, requiring the intense energy of stellar collapse to fuse silicon into iron through rapid nuclear reactions." Dr. Jennifer Johnson at Ohio State University studies stellar nucleosynthesis, the processes that create elements in stars. Her research traces the cosmic chemical evolution that made planets and life possible. She points out that early galaxies, those detected by JWST from the first few 100 million years of cosmic history, couldn't have had planets like Earth because they lacked sufficient heavy elements. Those elements had to be created over multiple generations of stellar evolution, scattered through space by supernovae and stellar winds, incorporated into later generations of star formation. This means you are temporally connected to cosmic history. You couldn't exist in the early universe. You required billions of years of stellar chemistry to create the elements needed for your existence. The universe had to mature, had to cycle matter through multiple stellar generations, had to create the conditions for rocky planets and liquid water and complex chemistry. You are not just in the universe. You are a product of its evolution, a structure that could only arise after sufficient cosmic development. To put this in perspective that highlights the intimacy of the connection, Consider a single calcium atom in your bones. That atom was created roughly 5 billion years ago in a supernova explosion, blasted into space at thousands of kilometers per second, cooled, and incorporated into the molecular cloud that would become our solar system 4.6 billion years ago. Gravitationally collapsed into the forming Earth, cycled through geological processes, eventually incorporated into living organisms, passed through food chains, and finally assembled into your skeleton. That atom has a history spanning billions of years and light years of space. It has been part of interstellar gas clouds, planetary crust, ocean water, ancient organisms, and now you. When you die, it will be returned to the environment, potentially incorporated into future organisms, continuing its journey through matter cycles. You are not possessing these atoms. You're borrowing them temporarily from a cosmic circulation that extends across space and time. But here's the isolation side of the paradox. Despite this deep material connection to cosmic processes, you are causally disconnected from most of the universe right now. Events occurring in galaxies beyond the cosmic event horizon have no causal relationship to you. They cannot affect you, and you cannot affect them. Not today, not ever. The expansion of space has created absolute separation. Regions of the universe that are physically real but might as well not exist from your perspective because no information or influence can flow between you. This creates a strange philosophical situation. You are made from universal matter, following universal laws, embodying universal processes. But you're experiencing all of this from a specific, bounded location in space-time, a local bubble that's increasingly isolated as cosmic expansion accelerates. You're connected to cosmic history, but disconnected from cosmic simultaneity. The 2024 measurements of cosmic expansion reveal that this isolation is intensifying. The dark energy, spectroscopic instruments' mapping of galaxy distributions shows that the rate of expansion is not constant, but appears to be changing over time, possibly accelerating faster than previous models predicted. If this trend continues, the cosmic event horizon will move inward in co-moving coordinates, meaning fewer and fewer galaxies will remain within our causal reach as time progresses. Dr. Adam Rees, who shared the Nobel Prize for discovering cosmic acceleration, has described this as living in a universe that's slowly closing its curtains. We can observe the distant past of galaxies now crossing the event horizon, but we're losing the ability to observe their futures. The informational connection is being severed by expanding space-time, leaving us increasingly isolated in our local cosmic neighborhood. Consider what this means for the long-term future of intelligence. If consciousness persists on cosmological timescales, perhaps uploaded into durable computational substrates or spreading to other star systems, it will witness a progressively emptying cosmos. Distant galaxies will fade from view, redshifted into invisibility. The cosmic microwave background will cool and dim below detectability. Eventually, only the local group will remain visible, a small island of a few dozen galaxies, surrounded by expanding emptiness. Any intelligence existing at that far future time will be isolated in ways we can barely imagine. They won't just lack the ability to visit distant galaxies, they'll lack evidence that distant galaxies exist at all. All the cosmology we're discussing now, the understanding of cosmic expansion and the Big Bang and large-scale structure, could become unverifiable, reduced to ancient historical retry-a-continue records with no way to confirm them through observation. Future beings might regard our cosmological knowledge the way we regard ancient mythology, as interesting stories that cannot be tested. Imagine you're living in a house, and every day one of the windows gets boarded up permanently. At first, you have views in all directions, seeing neighbors and distant landscapes. But gradually your view narrows. One window closes, then another, then another. Eventually, you're left with only a few windows showing your immediate surroundings, and you know that given enough time, even those will close. You're not being physically imprisoned, You can still move freely inside your house, but your connection to anything beyond your walls is being progressively severed. That's the future of consciousness in an accelerating universe. Not destruction, but isolation. The material connection remains, you're still made of matter following physical laws, but the informational connection is being cut, leaving you increasingly alone with only your local environment for company. Yet there's something profound about this connected isolation that transcends the bleakness. You are simultaneously the universe observing itself in a localized perspective, experiencing a limited view of that universe. Every thought you have is the universe thinking through one of its temporary configurations. Every observation you make is the universe becoming aware of itself through your awareness. The isolation doesn't negate the connection. It contextualizes it. Dr. Alan Watts, philosopher and interpreter of Eastern thought, described this as the field theory of awareness, where individual consciousness is not separate from the universe, but a localized intensification of universal process. You are not in the universe as a marble is in a box. You are the universe taking a specific form temporarily. The way a wave is the ocean, taking a specific form temporarily before returning to the general flow. This perspective transforms the meaning of cosmic scale. The universe's vastness is not something external to you that dwarfs you. It's the context from which you arose and to which you're intimately connected, even as you experience it from a specific, limited viewpoint. The isolation is real, bounded by physics and expansion, but the connection is equally real, extending through material composition, causal history, and the fundamental identity of your matter and energy with cosmic matter and energy. Consider your direct experience right now. You're aware of these words, processing information, generating understanding. That awareness is not happening separate from the universe. It's happening as a universal process, electrons moving through neurons, photons striking retinas, electromagnetic fields propagating through brain tissue. Physics is not describing something happening to you. It's describing what you are, processes temporarily organized into the pattern that generates your subjective experience. The universe is 93 billion light-years across in its observable extent, possibly infinite beyond that. But it's also the few pounds of matter in your skull organizing itself into awareness, the local intensification of universal process into consciousness. Both descriptions are true simultaneously. The cosmic scale doesn't diminish the local experience. If anything, it amplifies it, because it reveals that consciousness is a rare and remarkable achievement, a configuration of matter that the universe only occasionally manages to create. You are connected to everything through matter, energy, and physical law. You are isolated from most things through light speed, cosmic expansion, and causal boundaries. Both are true, both matter, and understanding both simultaneously is perhaps the closest we can come to grasping our actual relationship to the cosmos. So we're connected to everything yet isolated from most things, made of universal matter yet trapped in a local perspective. But this raises a final crucial question. Given this strange situation, what are we supposed to do with the knowledge of cosmic scale? Chapter 10, Living with Vastness. The knowledge of cosmic scale is not neutral. It changes you. Once you truly understand that the observable universe is 93 billion light-years across, that it contains 2 trillion galaxies, that it might be an infinitesimal fraction of an infinite cosmos, you cannot return to your previous perspective. The question becomes, how do you live with this knowledge? How do you integrate cosmic vastness into everyday existence? Let's start with what doesn't work. Nihilism, the belief that nothing matters because we're insignificant specks in an uncaring cosmos, is a common first response to cosmic scale. If the universe is this vast and we're this small, the reasoning goes, our actions and concerns are meaningless. But this conclusion mistakes physical scale for philosophical significance. It confuses size with value, assuming larger things matter more than smaller ones. Consider the alternative framework. Meaning is not discovered in the universe. It's created by conscious beings through their choices and relationships. The universe doesn't assign significance to anything. Conscious entities generate significance locally through their experiences and interactions. The fact that this meaning generation happens in a vast cosmos doesn't negate it. If anything, it makes it more remarkable, because consciousness is apparently rare and fragile, requiring very specific conditions to arise and persist. Dr. Rebecca Goldstein, philosopher and novelist, has written about what she calls existential vertigo, the disorienting feeling that comes from confronting scales far beyond human experience. She argues that the antidote is not to deny the scale or retreat into comfortable fictions, but to embrace what she calls cosmic humility, recognizing our actual position without letting it paralyze us. We are small in cosmic terms, but we are the parts of the cosmos that know we're small, that can understand cosmic scale and ask questions about meaning. That capacity itself is significant. The 2024 discoveries make this especially relevant right now. JWST's detection of impossibly early galaxies, DESI's mapping of cosmic expansion, the refined measurements of dark energy evolution, all of these reveal that we're living in a pivotal moment of cosmological discovery. We're the first generation of humans to have accurate knowledge of cosmic scale, to understand that the universe is 93 billion light-years across, to know that we're isolated in an accelerating cosmos, to grasp that most of what exists will forever remain beyond our reach. Previous generations lived with comfortable ignorance or wild speculation. Ancient peoples thought the universe was thousands of miles across, perhaps extending to the sphere of fixed stars. Medieval scholars debated whether the cosmos was finite or infinite, but had no empirical basis for choosing. Even 20th century astronomers thought the Milky Way was the entire universe, until Hubble discovered external galaxies in the 1920s. We're the first to see the actual scale clearly, and that knowledge carries responsibility. To put this in perspective that connects to your immediate life, consider how you make decisions. You choose what to eat, who to spend time with, what work to pursue, what values to uphold. Do any of these choices require the universe to be small for them to matter? Does your relationship with loved ones become less meaningful because those relationships occur in a cosmos 93 billion light-years across? Does curiosity become less valuable because most of the universe is forever beyond investigation? The answer is clearly no. The meaning of your choices derives from their local effects, from how they impact your experience and the experiences of beings in your causal network. The cosmic scale is context, not judgment. It tells you where you are, not what you should value. Integrating cosmic vastness into your worldview means keeping both perspectives simultaneously. You are cosmically small, locally significant, materially connected to universal processes, causally limited to a specific region of space-time, temporary in cosmic time, meaningful in experiential time. But there's another dimension to living with vastness that goes beyond personal meaning. The cosmic scale suggests that if intelligent life exists elsewhere, and if the universe is truly vast or infinite, then all possible experiments, all possible observations, all possible thoughts and experiences are being generated somewhere. This creates what philosopher David Lewis called modal realism, where all possibilities are actualized somewhere in the cosmos. If this is true, then the questions we're asking right now have been asked countless times across cosmic history by other intelligences in distant galaxies. The same curiosity, the same wonder at cosmic scale, the same struggle to integrate vastness into meaningful existence, all of it playing out in parallel across immense distances and time periods. We're not discovering unique truths. We're participating in a universal pattern, consciousness arising and contemplating its context, that repeats throughout space and time. Dr. Frank Drake, who created the famous Drake equation for estimating the number of communicative civilizations in our galaxy, spent decades thinking about how cosmic scale affects the probability of contact with other intelligence. His conclusion was bittersweet. If life is common, the universe is full of consciousness, but the vast distances and limited light speed make contact nearly impossible. We might be surrounded by billions of civilizations, each isolated in their local cosmic bubble, each asking the same questions about significance and meaning, never able to share their answers across the cosmic voids. Consider what this means for humanity's long-term future. We have perhaps 1 billion years before the sun becomes too hot for Earth to remain habitable, maybe 10 trillion years before the last stars burn out, maybe infinite time if consciousness can find ways to persist through cosmic dark ages. During that time, we could spread to other star systems, other galaxies in our local group, creating a technological civilization spanning millions of light years. But even that vast expansion would remain confined to a tiny bubble in cosmic terms, an island of consciousness surrounded by an expanding ocean of causally disconnected space. The knowledge of cosmic scale should inform how we approach that future. We're not building a galactic civilization that will dominate the universe. We're creating a local pocket of complexity and awareness that will persist for some finite time before entropy and expansion eventually isolate and extinguish it. That's not depressing. It's clarifying. It means the value of what we create derives from the experience of creating it, and the experiences it enables, not from cosmic permanence or universal dominance. You cannot change the universe's size. You cannot stop cosmic expansion or reach beyond the event horizon. But you can choose how you respond to this knowledge, whether you let it crush you into meaninglessness or inspire you to create local meaning precisely because the cosmos provides no external purpose. The universe is vast, indifferent, governed by impersonal physical laws. Consciousness is rare, aware, capable of generating purpose through its own activity. Living with vastness means holding both truths simultaneously, letting cosmic scale inform your perspective without dictating your values, recognizing your true position in the cosmos while creating meaning within that position. The universe is 93 billion light-years across. You are here now, aware of that fact, experiencing this moment. Both facts matter. Both should shape how you engage with existence. So we've discovered how big the universe actually is, explored the boundaries of observation and causality, grappled with significance and isolation, and considered what it means to live with this knowledge. But what does all of this leave us with? The challenge of living with vastness extends beyond personal philosophy into practical questions about humanity's future trajectory. If we understand that we're isolated in an expanding bubble, that most of the universe will forever remain beyond our reach, how should that knowledge shape our approach to space exploration? Scientific research and long-term planning? Consider the current state of human civilization. We're confined to a single planet orbiting an average star in an unremarkable region of one galaxy among trillions. Our furthest spacecraft, Voyager 1, launched in 1977, has traveled only about 0.02 light-years from Earth after nearly 5 decades. At that rate, reaching even the nearest star, Proxima Centauri at 4.2 light-years away, would take over 100,000 years. The scale of even our local cosmic neighborhood dwarfs our current technological capabilities by margins that seem almost deliberately designed to humble us, yet understanding cosmic scale doesn't argue for abandoning exploration. If anything, it argues for urgency. We have perhaps 1 billion years before Earth becomes uninhabitable due to the sun's increasing luminosity. That sounds like an enormous time span, and it is by human standards. But in cosmic terms, it's a brief window. If consciousness is going to spread beyond its origin planet, if human descendants or our technological successors are going to establish themselves across multiple star systems, the work must begin now because the scales involved require thinking in time frames of thousands or millions of years. Dr. Martin Rees, the Astronomer Royal of the United Kingdom, has written extensively about what he calls the cosmic endowment, the total resources potentially accessible to an expanding civilization. Even limited to light speed travel and confined to our local group of galaxies, A technological civilization could potentially spread across millions of light years, establishing itself on billions of planets, creating a network of consciousness and culture vastly larger than anything that's existed on Earth. The cosmic scale that seems so overwhelming actually represents possibility, not limitation, when viewed through the lens of deep time. But here's where the knowledge of cosmic acceleration becomes critical. We don't have infinite time to expand. The local group is gravitationally bound and will eventually merge into a single structure, but everything beyond it is receding. The Virgo supercluster, the larger structure we're part of, is not gravitationally bound. Those galaxies are already moving away from us due to cosmic expansion, and within a few tens of billions of years, they'll cross the event horizon and disappear from view forever. This creates what cosmologist Paul Davies calls the cosmic isolation deadline. If humanity, or its descendants, want to establish presence in galaxies beyond the local group, they need to reach those galaxies before cosmic expansion carries them beyond the causal horizon. Once a galaxy crosses that boundary, it becomes not just unreachable but unknowable, forever separated from our causal network. The expansion of space creates an actual deadline for cosmic exploration, measured in tens of billions of years perhaps, but a real deadline nonetheless. To put this in perspective, using a metaphor that captures the urgency, imagine you're standing on a dock as boats slowly pull away into fog. You can see dozens of boats right now, but they're drifting farther apart. If you want to reach one of those boats, you need to act while it's still within swimming distance. Wait too long, and the fog will swallow it completely, leaving you with no way to even know where it went. The boats don't disappear suddenly. They fade gradually, giving you time to make decisions, but eventually the opportunity closes permanently. That's humanity's situation with regard to distant galaxies. We can observe them now. We can study their properties, calculate their distances, understand their evolution. But cosmic expansion is carrying them away, and at some point in the future they'll cross beyond reach. Any civilization that wants to spread beyond its local cosmic neighborhood must do so while those neighborhoods remain accessible. This knowledge should fundamentally shape how we think about technological development and long-term planning. The usual framework for thinking about the future focuses on centuries or maybe millennia. Climate change, resource depletion, artificial intelligence, these concerns play out on timescales of decades to centuries. But cosmic scale demands thinking in millions or billions of years, recognizing that the decisions we make now about exploration, about preserving and spreading consciousness, about developing technologies for crossing interstellar distances, these decisions have implications that echo across cosmic time. Dr. Elon Musk has framed his work on space exploration as making life multiplanetary, arguing that consciousness is too precious to risk on a single planet vulnerable to extinction events. But the logic extends farther. Making life multistellar is even more robust, spreading across multiple star systems to survive stellar evolution. Making life multigalactic, establishing presence in multiple galaxies before they drift beyond reach, is the ultimate expression of this principle, ensuring that consciousness persists even as individual stars and galaxies age and die. You might be thinking this all sounds absurdly ambitious for a species that's barely managed to send a few people to the moon, and you'd be right to be skeptical. The engineering challenges of interstellar travel, much less intergalactic travel, are staggering. But the point isn't that we should attempt these things now. The point is that understanding cosmic scale means understanding that if these things are ever going to happen, they require very long-term thinking and sustained effort across many generations. Consider the cathedral builders of medieval Europe. They began construction projects that would take centuries to complete, knowing they would never see the finished structure. They worked on behalf of future generations, creating something that transcended individual lifespans. Cosmic exploration requires that same intergenerational perspective, but extended across timescales thousands of times longer. We're not building cathedrals, We're potentially building the foundations of a civilization that could persist for billions of years across millions of light years. And that foundation must begin with decisions we make now about what to value and pursue. But there's another dimension to living with vastness that's more immediate and personal: how it affects your moment-to-moment experience of being alive. When you internalize cosmic scale, when you truly grasp that you're a temporary arrangement of matter in a cosmos 93 billion light-years across, it can create what psychologists call dissociation, a feeling of being disconnected from immediate experience, watching your life from a distance as if it's happening to someone else. This is actually a danger worth addressing directly. Cosmic perspective can become cosmic paralysis if you're not careful. The solution is practicing what philosopher Thomas Nagel called alternation of perspectives, the ability to zoom between cosmic and personal scales fluidly without getting stuck in either one. When you're making everyday decisions, dealing with relationships, pursuing work, experiencing pleasure or pain, those things matter on human scales and should be engaged with fully. When you're contemplating existence, studying cosmology, thinking about humanity's long-term future, that's when cosmic scale becomes the relevant frame. The mistake is applying cosmic scale to human scale concerns or vice versa. Your relationship difficulties don't become less real or important because the universe is vast. The universe's vastness doesn't become less real or important because you're worried about relationship difficulties. They're different scales requiring different perspectives, and wisdom involves knowing which perspective to apply when. Dr. Viktor Frankl, psychiatrist and Holocaust survivor, wrote about finding meaning in even the most dire circumstances by recognizing that suffering can have purpose if we choose to give it purpose. His insight applies to cosmic scale as well. The universe doesn't provide meaning, it provides context. Conscious beings create meaning through their choices and interpretations. Understanding cosmic scale gives you accurate context for those choices, but doesn't determine what choices you should make or what meaning you should create. Think about a moment of genuine joy you've experienced. Perhaps connecting deeply with another person, or experiencing beauty in nature, or achieving something you'd worked toward for years. In that moment, did it matter that the universe is 93 billion light-years across? Did cosmic scale diminish the experience? Almost certainly not. The joy was complete in itself, valid on its own terms, meaningful precisely because you experienced it regardless of the cosmic context. That's the key insight for living with vastness. Cosmic scale is context, not judgment. It tells you where you are and what surrounds you, but it doesn't tell you what to value or how to live. Those decisions remain yours, to be made based on your experiences, relationships, goals, and the local network of meaning you're embedded in. The vast universe is not weighing your choices or measuring your significance. It's simply the stage on which your temporary existence unfolds, and that stage being unimaginably large doesn't diminish the reality of what happens on it. So live with dual awareness. Maintain cosmic humility about humanity's place in the universe while maintaining personal engagement with your immediate experience. Recognize that we're isolated in an expanding bubble while appreciating the material connection to cosmic processes. Understand that consciousness is rare and temporary while celebrating that it exists at all and that you're experiencing it right now. Hold all of these perspectives simultaneously, letting them inform rather than determine your engagement with existence. The universe is 93 billion light-years across, and you are here now aware of that fact, capable of holding that vastness in your mind while still experiencing the immediacy of this moment. That capacity for dual awareness, for thinking cosmically while living locally, is perhaps the most sophisticated response consciousness has developed to the challenge of existing in something this unimaginably large. Throughout this journey, we've discovered that the universe is 93 billion light-years in diameter, vastly larger than the 13.8 billion light-years you'd expect from simply multiplying its age by the speed of light. We've learned that this expansion is accelerating, driven by mysterious dark energy, creating event horizons that make 94% of currently observable galaxies forever unreachable, even at light speed. We've explored how the 2024 discoveries from JWST revealed impossibly early galaxies, suggesting the universe beyond our horizon is far more structured and complex than we predicted. But perhaps the most profound insight is this: cosmic scale doesn't determine significance. Consciousness, awareness, and local meaning generation do. The universe you live in is not the universe you were taught about in school. It's not a simple sphere of galaxies sitting in static space. It's a dynamic, expanding, evolving structure where space itself grows, carrying distant regions beyond any possibility of contact, creating permanent informational boundaries that limit what we can ever know. The observable universe is just one bubble in a potentially infinite cosmos, most of which will remain forever hidden behind horizons we cannot cross. But you are not diminished by this vastness. You are the universe becoming aware of itself, matter, organizing into consciousness, a temporary local intensification of cosmic process that can observe, understand, and create meaning. The atoms in your body were forged in stellar cores billions of years ago. The thoughts in your mind are electrical patterns following the same physical laws that govern galaxies and black holes. You are not separate from this cosmic immensity. You are an expression of it, a particular way the universe is manifesting right now, in this location, at this moment in cosmic history. As you go about your day, after watching this, remember that every breath you take cycles matter that has been part of stars, planets, ancient organisms, and countless other structures across billions of years. When you look at the night sky, remember that those distant points of light are galaxies containing hundreds of billions of stars, each possibly hosting planets, some perhaps harboring consciousness, asking the same questions you're asking now. When you feel small or insignificant, remember that significance doesn't come from size, but from complexity, awareness, and the ability to generate meaning through conscious experience. You are not an insignificant speck in an uncaring cosmos. You are a rare and remarkable configuration of matter that the universe only occasionally achieves, a local pocket of order and awareness in a cosmos trending toward entropy and isolation. Your thoughts matter because you experience them. Your choices matter because they shape your local causal network. Your existence matters because consciousness itself matters, being perhaps the rarest and most complex phenomenon the universe produces. The universe is 93 billion light-years across in its observable extent, perhaps infinite beyond that boundary. It contains 2 trillion galaxies, each with hundreds of billions of stars, creating a total of more stars than grains of sand on all Earth's beaches. It's been expanding for 13.8 billion years and will continue for trillions of years more, growing emptier and darker as acceleration carries distant structures beyond reach. Most of what exists is already unreachable, and more crosses the event horizon every second. But none of that changes the reality of your immediate experience. You are here now, aware of these facts, capable of wonder and understanding. The universe gave rise to conditions that allowed consciousness to emerge, and through your consciousness, the universe is observing itself, becoming aware of its own structure and scale. That's not insignificant. That's cosmically rare and philosophically profound. We live in a brief, bright epoch of cosmic history when stars shine, when galaxies are visible, when the cosmic microwave background still carries information about the Big Bang, when consciousness can arise and study its context. This epoch will pass. Stars will burn out, galaxies will drift beyond horizons. Eventually, only darkness and cold will remain. But that far future doesn't negate the present. If anything, it makes the present more precious. Because it's temporary, because this particular configuration of matter and energy into awareness and complexity will never occur again in exactly this way. If you made it this far, You've spent nearly an hour contemplating cosmic scale and philosophical implications. That's a remarkable use of conscious attention in a universe that mostly consists of empty space and simple physical processes. Consider hitting subscribe and giving this video a thumbs up if you appreciate deep explorations of cosmology and meaning. And check out my video on what happens at the edge of the universe, where we explore the strange physics at cosmic boundaries. I think you'll find it fascinating given what we've discussed here. The universe is bigger than we thought possible. It's more complex, more structured, more isolated into causal bubbles than previous generations imagined. We're living in the first moment of human history when we can see this scale clearly. When we have telescopes powerful enough to detect light from galaxies that formed when the universe was barely 3% of its current age. That privilege carries responsibility to understand accurately, to avoid both cosmic arrogance and cosmic nihilism, to recognize our actual position without letting it determine our values. You are made of star matter, following physical laws isolated in a local bubble of causality, temporary in cosmic time, meaningful in experiential time. The universe is vast. You are small. Both statements are true, and neither determines your significance. What determines significance is consciousness, awareness, the capacity to experience and understand and create meaning through your choices and relationships. Right now, at this very moment, light from the edge of the observable universe is reaching Earth after traveling for over 13 billion years. That light began its journey when the universe was young, crossing expanding space, stretching into longer wavelengths as it traveled, finally arriving here where it can strike a telescope mirror, be detected by instruments processed into images, studied by conscious beings trying to understand their cosmic context. You are one of those conscious beings. The universe is making itself known to you through ancient light, and you are making the universe known to itself through your understanding. That reciprocal relationship, played out across 93 billion light-years and 13.8 billion years, is what it means to be cosmically aware.